In general, our idea for an instantaneous rate of change is a good one, but there's a problem with it. And the problem is for most functions, this ratio that we're using to get at the instantaneous rate of change, right? We'd like to know what this is when b is equal to a. But when b is equal to a, these two pieces in the numerator are going to be the same. They're both going to be f of a. And in the denominator, of course, both pieces are the same, so we'll get a minus a. And so this ratio that we're using to get at the slope of our tangent line, in the case we're actually interested in, where b is equal to a, it always gives us 0 over 0. And 0 over 0 is undefined. It's tempting to say that this is, maybe it's infinity or maybe it's 0, but in fact, this particular combination of symbols could be almost any number, as we'll see later. So when we get 0 over 0, what that means is we're going to have to work harder, right? Even in a case like this, no matter what a is, right, anywhere on this graph, there is some slope of a tangent line, but this particular ratio, no matter what a is, right, there's always going to be a tangent line on this particular graph, but this ratio that we would like to use to calculate our slope is always going to give us 0 over 0, no matter what a is, no matter where we are on this graph. So what we really need is some way to approach b being exactly equal to a without actually just setting b equal to a. So the idea here is, if we have some particular a value, well, b will start off to one side, and then rather than just plopping b down on top of a, which gives us this 0 equals 0 problem, what we're going to do is slide b towards a, like this. And as long as b is never actually equal to a, then this ratio should be defined. And then we'll have to just watch what happens to the value of this ratio. Hopefully, right, our hope is that as b gets closer and closer to a, this ratio will get closer and closer to something. And whatever that something is, hopefully it's a number, whatever that number is, that will be the value of the instantaneous rate of change. So what we're going to have to do is get a handle on this idea of sliding one value towards another value and seeing what happens to some function. Right? And the name for that idea is a limit. So here's the notation that we'll use for that idea. The limit as x approaches a of f of x. So what all this means is we have some value, right? So there's this function. This graph here is supposed to be f of x. And we would like to know if x starts off to one side of a, but then we slide x towards a, what happens to the value of the function at x? Well, so if x is over here, the value of the function at x is way up there somewhere, but we're going to slide x towards this fixed number a. As we do that, this point, the spot on the graph corresponding to x, well, since we're sliding x towards a, this spot is going to slide along the graph. It's going to go this way in this case, over to, say, here. But then we keep sliding x closer to a. Now the key thing here is that x is never actually going to be exactly equal to a. In this graph, we can't have x equal to a because this function isn't defined at a. But we're just going to slide x closer and closer to a. You can see that if x starts off to the right of a and slides towards a, then for this particular graph, the value of this function, which is the height of this point, is getting closer and closer to this height, whatever height that happens to be. What if we started on the left? So what if x starts over here? Well, then the corresponding point on the graph is down here. And as we slide x rightwards towards a, well, now it's over here. And then it's over here. And then it starts to slide up here. And as x gets closer and closer to a from the left, the height of the corresponding point on the graph is heading towards this value. Well, that's the same value as from the other side, so these two sides agree. So this height, whatever this is, this y value, this is what we will call the limit of f of x as x approaches or goes to a. And this is the cluster of symbols that we'll use to denote this value. So the limit is just what the value that the function is heading towards as x heads towards the x value a. Right? And on the graph, we can clearly see this happening as we sort of slide towards a from both sides. The graph slides towards this height at the center. Right? Now, the key thing about limits, the reason that we are inventing this idea is because this definition of a limit, it doesn't depend on what happens exactly at x equals a, right? This whole phrase, none of this depends on what happens when x is actually equal to a. In fact, the function doesn't even need to be defined when x is equal to a. The only thing that matters is what happens when x is near a. Right? As we're doing this sliding process, x never actually gets to a. It's always sliding towards a. So it's getting closer and closer to a. So we're near a, but we're never at a. And that's the key thing about the limit. And remember, the reason that that's the key thing about the limit is because what we're ultimately going to be using limits for is to take the limit of this sort of slope quotient. And for this sort of slope quotient, we can never let b actually get to a, because then we just get 0 over 0. So the idea of the limit using the values of the function near a, but never at a, that's really the key detail that's going to make this whole thing worthwhile. Well, let's look at some examples of a limit. And we really only have, at this point, we really only have two ways of calculating limits. And one way is just to use a graph, like we did in the previous slide. So for example, let's find the limit as x goes to 5 of f of x for this graph. So this is a graph of f of x. All right, so we need to keep our eye on the x value 5. So that's playing the role of a here. So that's right here. So what we're going to do to evaluate this limit is imagine starting off to the left and then sliding rightwards towards 5. On the graph, that's going to start up here somewhere and slide that way. And then we'll start to the right of 5 and slide leftwards. And on the graph, that's here, and we'll slide up that way. And you can see that both starting from the left and starting from the right, we're heading towards this point on the graph, this blue point, and the height of that blue point is 2. And so this limit is equal to 2. In this particular example, 2 also happens to be the value of the function at 5. So for this particular example, what happens at 5 is the same as what happens near 5. But remember, the function doesn't have to be defined at 5 for this limit to be 2. As you know, if we punched a hole in the graph here, the limit would still be 2, even though the function would no longer be defined. All right. For another example, let's look at the limit as x goes to 3/2 of g of x. And this is a graph of g of x here. Well, we can do the same sort of visual calculations. Start off to the right, that's down here, and the point's going to slide this way. If we start off to the left of 3/2, which is 1.5, that's over here. Then the point on the graph is going to slide this way. And you can see that these are sliding towards the same height. They're both sliding towards this height. Now, since we're reading a graph, the best we can do is approximate what this height down here is. It looks like maybe it's 0.75-ish, something like that. So we have a value for this limit. But notice that this is the limit at 3/2, but f at 3/2 isn't even defined. So this is what I mean when I say that the limit uses the value near 3/2, but never at 3/2. f of 3 halves doesn't even make sense, but sorry, not f, g. But the limit at 3 halves is perfectly well defined, and it's about 0.75. There actually is another way besides just using a graph that we can get a handle on what a limit is, and that is just by plugging in numbers. So, graphically what we were doing is starting near our a value and sliding towards it from both sides, but we can do the same thing sort of numerically by just plugging in x values that are close to our value for a. So for this particular limit, the limit as x goes to 2 of 4x minus 8 over x squared minus 3x plus 2, we can just plug in values near 2. So let's do that. Let's pick some x values that are close to 2, and then we'll calculate 4x minus 8 over x squared minus 3x plus 2. And the idea is we're going to start near to 2, but then we're going to plug in values of x that are closer and closer and closer to 2, and we'll see what happens. So maybe we'll start with 2.5, and we'll punch it into a calculator or something, and you get something like 2.667 if we round it a little bit. Okay, so we're close to 2. Remember, we're plugging in values close to 2. 2.5 is kind of close to 2, but not really, so let's get much closer. How about 2.1? If we plug that into this function, we get 3.6364, something like that. So now the number that we plugged in is only a tenth away from 2, but still that isn't very close. So how about we plug in 2.01? Then we get 3.9604-ish, about that. But again, a hundredth away in the grand scheme of the real numbers. A hundredth is actually kind of big, so let's maybe plug in 2.001. That gives us 3.996004 and change. And even that isn't very close to 2, so why don't we plug in let's see, the next one that I did had 6 zeros, so 1, 2, 3, 4, 5, 6. Now we're getting pretty close to 2. This is 3.999996965. Anyway, you get the idea. So now what we can do is ask ourselves, our goal is to figure out what are these values getting close to? What are they approaching? Well, it looks like they're approaching 4. So our approximation for this limit would be 4. Now, we don't actually know if it's exactly 4, right? This is pretty good evidence that the limit is close to 4, but we haven't plugged in every number near 2. We've only plugged in a few. So this is really just an approximation. It's essentially an educated guess. All right, for a final example, let's find the limit as x goes to 3 of h of x. And this function here is h of x. So we'll do what we have been doing. We'll start, so our a value this time is 3, so that's right here. So we're going to start to the left. The corresponding point on the graph is here, and then we're going to slide towards 3. So our point on the graph slides up that way. And then we'll start to the right, so maybe over here near 4. And then we'll slide leftwards towards 3. The corresponding point on the graph slides up the graph this way. And, well, these two coming at 3 from each direction, they don't actually agree on the height, right? If we come at it from the left, it looks like we're heading towards height 3. And if we come at it from the right, it seems like we're heading towards height 2. But when we wrote down our idea for a limit, we seem to be implying that there should be a single value that we're heading towards. But here we don't have a single value. It looks like there are actually 2 values. So this limit, I guess we should say that this limit doesn't actually exist. There's no single number that we can call the limit. So this limit does not exist. Okay, so if we have a limit that doesn't exist, we can write DNE for short, just because does not exist has too many letters in it. But this shows us that our idea of a limit, it isn't something that will always exist, right? The problem with this particular function was that there's this jump here, right? So coming at it from the two sides gave us two different values. There are actually a few other ways that a limit can fail to exist. So our previous example of how a limit failed to exist, this is called a jump. I guess I'll just call it a jump for now. Because, right, there's this gap here. There's this jump where the function is heading towards one value and then it jumps to another value. Another way that a limit can fail to exist is if we have something like this. Right? So here, this limit, if we think about the limit as x goes to 0 of f of x in this picture, this limit fails to exist because as we approach 0 from the left, the graph goes up. As we approach 0 from the right, the graph goes down. Well, these two are never going to come together to agree on a height, and so this limit does not exist. Okay. But there's another way that a limit can fail to exist. Let me get another copy of this image here. Another way that a limit can fail to exist is, suppose that we have a graph that comes in like this, and well, so I'm going to ask ultimately about the limit as x goes to 0 of the graph that I'm drawing. Now let me draw the graph. So if it goes like this, right? So now I know what you're waiting for me to do is see how draw the part that connects this graph up to the y-axis, because that's where x is 0. But as this graph approaches the y-axis, what I'm going to make it do is just go up and down forever, like this. And the closer we get to 0, the more this goes up and down. And then the same thing from the right. It comes in from the right, and then, it comes in from the left, and then the closer we get, the more it bobs up and down like this. Now this function is perfectly well defined everywhere except 0. In fact, I could even write a formula for a function that does that. If you pull up your favorite graphing tool and graph sine of 1 over x, you'll see a graph that looks essentially like this. But now we can think about the limit. Is there any single height that this graph gets close to? Well, clearly not. You can sort of see that it gets close to all of these heights on the y-axis. So there's no single value that this is zeroing in on, and so this limit does not exist.